and much for inviting us. Our next speaker is Professor James Gattiker from Los Alamos National Laboratory. He works in data science, verification, validation, uncertainty quantification, and computational statistics. At Los Alamos, he works with the groups of computer and information sciences, non-proliferation safeguards and security, nuclear weapons, and statistical sciences. And he will deliver the talk, Complexity Challenges in Uncertainty Quantification for Scientific and Engineering Applications. Thank you, sir.
Thank you. Great to be invited to be here. Thanks for having me. It's certainly an interesting, illustrious tradition to be at the Isaac Newton Institute. So I'm in the Statistical Sciences group at Los Alamos. I'm the group leader now. And I'm going to start the discussion here with some background about uncertainty quantification challenges and applications that we go through at Los Alamos and why we're interested in uncertainty quantification. And that's to start out the workshop here. I hope I'll see you all in the hallways and be able to have the conversations about methods and details of the methods that we all want to have at the workshop here. Los Alamos National Laboratory is where I'm from, established in 1943, of course, as the Site Y of the Manhattan Project, which was focused on building the first atomic bomb. Let's see, so why did that happen? That was it. All right. Let's see. Yeah, some EMP. So it's still a large laboratory. It's gotten to be a much larger laboratory. Its mission is to solve national security challenges and global security challenges through exploring the basic underlying science. It's one of the largest laboratories in the world, 11,000 people, 1,200 employees almost, and 20% PhDs. So a lot of scientific applied science goes on at Los Alamos. In that, there's a history of computing. From the very early on, automatic calculators you can go through those. So one of the early general purpose computers, and adopting the computational platforms as they're developed through time up to our current 10 petaflop class machine, and exploring things like the D-Wave machine, which are quantum annealing machines, which give us alternative views of computation and thinking about what computation is out. And that's the mission of the laboratory, is not just to use computers, but to think ahead about what scientific computing might be, as well as all the underlying physical sciences. The point of going through all that is, there's two things I want to say about this slide. So one is we use these computational resources, and have always had a history of using these computational resources for supporting science. And so that's really what fundamentally uncertainty quantification is about. It's about using complex models and trying to fit those into the scientific and engineering discovery process. And so that's where we are with UQ, is that we're very much concerned with how we understand those models, how we use those models, and how we use those to support the science and engineering that we need to do. The other point on this slide is that there's the left column is statistics, the right column is UQ, and I want to distinguish those two things. Whereas if you take a cursory look at UQ, you might say, well, what's the difference between UQ and statistics? Statistics is about working with uncertainty. And we say that UQ is understanding the reliability prediction using the scientific computational models. So I think that's an important distinction to make when we're talking about the statistical view of UQ. And if I wasn't clear enough at the beginning, my view on these things is the statistical view of UQ. I'm looking forward to talking more to the applied mathematicians about their view of UQ. So we have a number of applications in statistics, reliability, classic statistics, how do we deal with data, how do we deal with detection and discovery, and then a number of applications, and this is just some quick survey of applications that we're involved in that use complex computer models in order to support science and engineering inference. So after that introduction, I'm going to go through two segments here. One is looking at a complicated science and engineering model and talking about the challenges that I see there, challenges that inspire difficult problems. And then the second is a particular one about response modeling, multivariate response modeling. Before I get into this one, I think the issue in the complicated science models is, as I said here, I alluded to Tukey's quote, one of the nice things about statistics is we get to play in everybody's backyard, so we get to play in all these interesting applications. And it's those interesting applications that suggest research issues to us that need to be addressed. So we gain inspiration from those. I'll start with this very general conceptual framework for statistical analysis with simulations. And it has the classic aspects. In the middle of it, as I said, in UQ is a computer model. We have to expect that computer model is not accurate to the real system. We have a system configuration which says what that computer model is supposed to be doing, so what particular system it's supposed to be modeling. Typically of interest, we have uncertain parameters. That combination gives us system predictions that we then compare to experimental observation. So that's, as I think of it, the most general framework that we can kind of come out of that. And from the statistics point of view, when we have that framework, we can solve all of the sorts of problems that we're interested in, or at least many of those, or start to address all those problems, which is, say, learning about the model error delta here. If we know something about okay, so this is going to keep going on. If we know something about, so should I try connectors or? Okay, I'll keep trying this. Maybe somebody will help out. If we know something about experimental observations and something about our parameters, we can learn something about the model discrepancy. If we know something about our parameters and about our model discrepancy, we can do something like predicting aspects of the system. The idea is we have some knowledge about some parts of this system and unknowns in other parts of the system, and we can do this inference more generally. And so I personally don't think about this as necessarily being a different problem for forward propagation in UQ or for inverse propagation in UQ. It's about the understanding that this system is characterized. And of course, different tools come into play. And ultimately to support design of experiments. Another general comment on these systems, this is a picture from the U.S. National Academy's report about assessing reliability of complex models, but it's the traditional picture of verification and validation and how different parts of this system relate. In particular, there's typically a mathematical model describing the system, a computational model implementing that mathematical model, samples from the system, and really a loop that describes the science and advancement process that we have. Verification, and if you've heard the term V&V, verification and validation, verification is this step about is the mathematical model being correctly implemented or adequately implemented by the computational model? Is the validation, is the computer model matching or adequate for modeling the true system in whatever aspect we're interested in? That's validation. And then another step, which is the really important step, which is going from all those things to refining the models that we have in order to advance our understanding. So it's difficult to separate validation, verification, and uncertainty quantification. Uncertainty quantification supports all of these steps, I think. Jumping into an application goal to describe this, I'll talk a little bit about the carbon capture project that I work on with some other people at the laboratory. And this is the idea of taking post-combustion, when you're burning fossil fuels, if you can capture the carbon dioxide, it's something we'd like to do. It's a process that's very complicated. This is a picture of just a test facility, which has a little pilot plant and a place for it's a user facility. People can come and bring their apparatus and build complicated machinery to do carbon capture in order to characterize that. So that's just the test facility. Although carbon capture as a chemical process is likely feasible, it's going to be certainly a large undertaking as it gets going. So where are we in the state of development? We're wrong button. We're currently evaluating alternative processes in chemistry. And what that means is we have a complicated chemical process here. We have different potential solvents, different potential aspects of the process. And what we want to do is optimize that process. So for capture efficiency, how much CO2 can we get out of the exhaust stream? What's the energy loss on the facility? What's the plant cost? All those things need to be optimized. The project goal overall for a project like this is to talk about how do we get there? How long does it take to get there? Obviously, we'd like to get there sooner than later. And the notion is, when we get into this with scientific and engineering models and the UQ, or the VV-UQ, verification, validation, and uncertainty quantification framework, we would like to accelerate what that process construction is. So how long does it take to build up a complicated chemical process engineering framework from basic science to production? A couple decades plus, maybe, historically. And we'd like to really accelerate what that is using physical simulations and aiming for far shorter times in order to construct a mature technology. And that really is where UQ comes into the perspective of science and engineering. So the conceptual framework I showed earlier had a single computer model, a single modality of observations, a few parameters perhaps, and that's the nice example for being able to solve these problems and something that's tractable. When you look at a complicated process like this, I could say that there's many levels associated with a chemical process model and the kind of development into mature engineering facilities. The first one is chemical process models, where lab work and basic physical property measurements and models of those things supported by uncertainty quantification lead to understanding of physical properties. For example, chemical kinetics. How do chemicals interact? How does the solvent capture CO2? Diffusivity, how does a gas dissolve into a liquid? Viscosity, things like that are basic lab benchtop measurements, properties models, but still have models and some measurements and some parameters to calibrate. All those things have to do. This picture is a conceptual model of what's called a wetted wall column. If anybody's a chemical engineer here, any chemical engineers? Increasingly chemical engineers are involved in UQ, and mechanical engineers and others. No hands up, so we can, I can safely talk about chemical engineers, I guess. So a wetted wall column is a apparatus that you can buy that runs a thin film of a solvent over a cylinder, and you put a gas that flows through that. The liquid comes out, gas goes in, some of the gas goes into the solvent and is captured. So in addition to these basic properties models, the next level, this benchtop apparatus, explores something about the integrated behavior, also introducing several parameters and several additional aspects of uncertainty and uncertainty quantification. When we're thinking about a full carbon capture system, the liquid that's flowing through this is going from one reservoir to another reservoir, the gas similarly. You might want to have a whole apparatus of an idealized full system in a larger sort of lab model, which includes both capturing something in a more real context, getting it back out in a more real context, because of course the whole point is to get the carbon dioxide back out of the system, which includes further parameterized physical relationships. And there might be levels of exploration like this as you're exploring complex systems. The final level, of course, is the actual system that you want to build. And that's what you want to both characterize and, unfortunately, the reality is that you're extrapolating to the actual system. So that's always a challenge in these sort of systems. And when you start thinking about that simple conceptual diagram and what that looks like in this system, if you think of a two-layer system, you're looking at and I'm not going to go through this whole diagram, but you're looking at a diagram that looks a lot more like this, a relationship between the information and aspects of this diagram. Whereas before we had one nice small segment of this, a process model that's compared to data in the face of some sort of discrepancy. In this case, you have a much, much more complicated system that we have to deal with. And so this starts to introduce some of what I think are the contemporary challenges of uncertainty quantification. So these are those individual process models, properties models that I mentioned before, for example, chemical kinetics and viscosity. And then we have this integrated into a wedded wall column model. Each one of these has some parameters. Some of those parameters are shared between these. For example, they all have a dependence on temperature, as does the full system model. There's discrepancies running around in all of those models. There's comparison to data within those models. There's discrepancy of the full system model, comparison to data of the full system model. These sorts of things start to get pretty complicated and difficult to analyze. And in the face of that, although you might imagine you can get a lot of data about chemical kinetics from benchtop experiments, it might take a day to run a wedded wall column model experiment for a setting of all these parameters, and suddenly you're very data limited. And so there's a lot of challenges in limitations of data, running the models, and of course, and I'm not going to belabor this, if you've been part of the workshop, I'm sure we've heard about emulator approaches and what the Gaussian process style analysis brings to the table in emulator methods, but there's emulators running around this whole thing too, so you need to approximate these models with emulators or surrogates, and that introduces a number of additional parameters. So we need methods for analysis and control of parameter interactions, and I'll talk a little bit more about each of these and what I mean by them. Nuisance distributions, coupling, emulators, functional calibrations, and discrepancies. So thinking about the challenges, analysis and control of interactions. As I said, there's potentially limited data, even in benchtop experiments, but certainly as you get to full system experiments, this data is very expensive to collect. And so you need to use this as efficiently as possible. If you have full system tests, obviously you're not going to be able to exhaustively test that. And as we go back to a system like this, the question is, what is the implication not only of the data associated with a particular parameterization to the parameters in that affect that is the calibration of those parameters, but what is the implication of the full system model to those parameters? Potentially that's in there, but of course there's not enough data to meaningfully use those as calibration targets. And so the challenge then is how to usefully and adequately and correctly, I guess, subset the calibration dependencies across models. There are some terms for this like blocking, or you might even say graphical models, but controlling, obviously if you have 2 data points, you're trying to calibrate 50 targets, you don't have a lot of information to do that. But which ones are most usefully used to do that? That's a complicated question of analyzing dependency structures across an entire complicated graph like that. Nuisance distributions are making this even more complicated, especially once you start blocking and segmenting this graph. And what I mean by nuisance distributions is parameters, which you might call an X in the previous model, which sets up the model, which we normally think of as point values, are in fact often distributions. You can think of them in priors and in particular analysis, but they might be expert priors, or they might be priors that are calibrated from a previous analysis, for example, a submodel analysis. And now we have all these stochastic distributions around that we have to take care of all of our operations in the face of that. Once the calibration dependencies are specified, when we're calibrating one target, the distributions of the others have to be accounted for. The simple solution, because I'm talking about Bayesian model calibration, we're relying on MCMC, Markov chain Monte Carlo techniques a lot. If you do that in a naive way, you're talking about having to integrate explicitly over these distributions, which can be complicated joint distributions in some cases, and for each target. So you draw an MCMC point proposal. You need to integrate over a number of distributions in order to establish the likelihood. Obviously, that quickly becomes computationally intractable. So are there better strategies? Are there better strategies? There are ways to deal with propagating distributions more directly through emulators, as long as you know the form of the emulators in some cases. Those quickly become complex questions. I'd say we're at the beginning of knowing how to do that. Part of that answer is in coupling, linking emulators. Emulators being the reduced complexity models. such as Gaussian process models that are fast analysis targets. I'll mention the last comment first. There's supposed to be fast versions of the models that we're using to support this analysis, but they're nowhere near fast enough to support the kind of integration we need to do that I was describing before. So in multi-level models, emulators can be used both as full system approximators and submodel approximators. There is work in propagating distributions. I'll call out Ksenia's work. She worked with us a bit a couple of years ago. Distributions can be propagated, but there's plenty of opportunity in calibration, distributions, design of experiments in order to address some of these challenges that I was describing. Another issue that we explore is how to do functional parameters, I'll call them, as calibrations. A simple so-called Arrhenius relationship in these process properties models that I was describing is going to be an exponential type model that looks like that, with up to 4 parameters depending on what their complexity is in their simplest form. Sometimes we know some of those in some ways. If anybody's worked with exponential forms of that case, the parameters are highly correlated. They're fairly difficult to work with. And to represent a simple function that looks maybe like this, where you have an ideal function in the middle, can be pretty complicated to infer if you're trying to deal with multiple of those at the same time. Can we find more efficient ways to work with a function than using parameterized functions directly? There's some work on this out there. In particular, prior constraints can be more intuitively expressed on the function, which is nice. It's very difficult for an expert to specify priors on that capture measurements or previous data in the literature. But if you can specify a prior by saying, oh, it kind of needs to be in this box, that's a more natural way to specify the limits on what those functions might look like. And if we can just, it would be nice to be able to realize what those functions are without having to go through an exhaustive analysis of correlated parameters. One of the challenges, of course, is that you can't directly, or we don't know how to directly introduce a constraint that makes a function look like that without explicit parameterization. One idea, some of the work that's out there, it says that monotonicity can be enforced. Is that a sufficient case constraint on realizations? That's an open question. Of course, when you deal with the subject matter experts within a physical domain, they don't like to have you departing too far from what they think is the actual functional form. The overall question here is, can constrained functionals be less complex to work with than parameterized functions? Something to go after. And this is really just a note. Discrepancy functions are notoriously difficult to work with. Physicists like to have discrepancies that they can understand, as I mentioned. Stochastic discrepancies are typically not sufficient to correct deficiencies of the simulations with a physical interpretation. And I'm sure nobody, including me, is guilty of ever just saying, oh, we'll just call that discrepancy. So this is a summary of this segment, just to say that multiple nested models are really, they're demanded for inference in complex science and engineering problems, the kind that I'm dealing with a lot. And connecting these science and engineering models, really I'm going to say is the essence of modern scientific and engineering processes. It's not going to get simpler, and just in the last few years, it seems that every enterprise of that character is moving towards having fundamental models that are bringing them along, whether they're the science type models, which we can defend as being on the side of the axis of very physically realistic, or engineering models, which are on the axis of perhaps more sort of properties models that are characteristic of physical systems, but not necessarily connecting to basic physics. And a couple examples that motivate us. Carbon capture is a good example. Materials design is an up-and-coming example where we're trying to bridge scales from science underlying models to achieve targeted bulk properties, say stress-strain relationships or strength models or electrical properties. Infrastructure models are very important. This goes from network science kinds of properties to resilience of critical infrastructure. So with those motivating problems, which I look forward to discussing with everybody across the workshop, I'm going to look at multivariate response, which is something I've worked in for a while, and the potential for bias and overcertainty and conflicting information, which is always a danger. Multivariate responses are difficult to connect to some of the UQ principles that we're very interested in. I realized, thinking about this slide just recently, that I missed the opportunity. So this is talking about, we're going to use an example of dropping objects from some tower and looking at what a model of acceleration and air drag is. I could have certainly used an apple hitting a guy on the head with the old apocryphal story. That would have been really good here, so you just have to imagine that I included that. The notion here is that we're dropping objects, and this kind of describes the science process that I was talking about. We have data, we have a simulation model. We might be able to fit the data with a regression model with very low information. It doesn't fit the data very well, but it's the first thing to do with exploratory data analysis. We might have a statistical and a simulation model. For example, a model of acceleration that fits the data maybe fairly well, but not quite, where the green is the model result, the red is the bounds after adding a discrepancy component. And the science loop, if you will, shows that is the notion that we try to improve our physics model by saying, oh, in fact, there's air drag going on, and when we include that component, then we're doing a lot better even when we model things with discrepancy. So that's the statistical UQ process in concept. So I'm going to follow this simple model for a bit and get into multivariate observations. So we have a model like this. If we don't understand that there's drag, we have a model that says as the object falls, it's going to go faster and faster. If we do have a model of drag, then of course it eventually limits out, and that's more like the blue one. The goal that we might have here, just as a simplified scientific process, is to infer G, gravitational constant, which is pretty easy if we have a perfect model, meaning that the model, the data that I have is simulated from the model with some error. And it's if you go through the calibration process, you get samples that recover G to the correct value within the limits of uncertainty, of course. I'm going to point out here, I'm using the word product likelihood because you can separate the individual observations along here as a product in the likelihood space. And that's characteristic of how we usually treat observations, as in independent, identically distributed observations, and we can take the product of those in order to get them out. And the prediction intervals in green, I think, are not going to be visible here, but they're quite tight, of course, on making model predictions. Now, naturally, if we have the wrong model, that is, the model is the one with atmospheric drag. The data has atmospheric drag because it's real data. The model doesn't have atmospheric drag. The data is the correct, the ideal model is the red one still. The data fit is the green one. The model fit, in this case, only weakly suggests that there's going to be any discrepancy with the data. The calibration of our parameter is quite wrong. And we don't really have any way to diagnose this. This is part of the issue that we typically face when we're doing uncertainty quantification in new problem areas, that discrepancy has to be either known or we face this idea of biased parameters. So in this case, I'm going to say that what if we have two different groups of observation, say one group down here, one group in here. We can consider them separately. If we consider them separately, the group that's down here gives us an accurate mean estimate with quite a bit of uncertainty because, of course, we're in an area where we're not nailing down the model that well. There's a high discrepancy group up here, or a group of data up here that has discrepancy. It gives us a very, very certain idea of what our parameter is, which is also quite wrong. Combining those two groups together, of course, gives us again, a very certain answer for what our inferred values are, which is wrong. And there's, again, not really a way to tell what the discrepancy in our model is in this case, which is problematic. And the reason I'm pointing out is that this sort of thing is really happening all the time. So I'm talking about a model framework including discrepancy that looks something like this. As I've been implying, in some cases it's possible to infer a discrepancy component when the model just doesn't meet the data at all. And so that's a nice case. If you have to have discrepancy, it's a nice case. There's a model of inferred observation error, a model and a systematic offset in the response, and we can say, okay, our model's not accurate. But in this example, neither of these things can be inferred from the data. And again, it's unrealistic to expect the discrepancy to be properly specified. If it were, we would put it into the model. Hierarchical models relax this assumption. And so this is, I'm proposing a potential way out of this sort of thing. What we would like to do is to have each one of these groups of observations be represented by a hierarchical component. So there's an index on our discrepancies now. But we, again, don't know what that discrepancy is. And so we need to recognize that, that there is, in fact, a relationship between discrepancy and parameter bias. And those things need to be, we need to acknowledge that there's a bias on each one of our parameters associated with this unknown discrepancy. So those two things together, I propose, really is model structural error. It's a relationship between response discrepancy and parameter bias. That model, of course, is not identifiable, meaning we can't infer what those are, as I've been advocating so far. But we can construct this as a hierarchical framework where we say there's some distribution on these thetas. We don't know what the discrepancy is, but we can start to talk about what's our uncertainty in the parameter space and try to put a so-called shrinkage prior on those, which says, given no problem with the data, we can fit parameters. Given problem with the data, we're going to have a distinction between inferred distributions. And so quickly, the punchline of when this sort of thing turns out is that when the model's correct with the system observations, in this case, perfect model experiment, using a system like this allows us to say, wow, we've inferred our parameter and we're pretty certain about it, just as we should be. When the model's not correct for the observations, the parameters and predictions are uncertain. So we cover the true value, but we're very uncertain about what that true value is because we can only do what we can with the observation. The trick is not to be in the case where you're getting, in this case, not knowing that you have discrepancy. And that's the intent of going through this entire model. Just as a comment on this whole issue can be thought of an issue of lack of fit. The likelihood is indicative. If you saw a very low likelihood, you would say, well, my model's not fitting well, maybe I have too much discrepancy and I'm not doing things correctly. But absolute likely values and complicated Bayesian systems, like that complicated structure I said, are not very informative. It's difficult to judge what the implication of that is. Of course, the usual prescription, simulating from the posterior model, is a good idea. But the hierarchical model can be considered a form of diagnostic that I think should be brought to these sorts of complicated problems when you're trying to infer parameters using data that has different qualities to it. The shrinkage prior really is a trade-off with the data likelihood and gives you some sort of idea of what the sensitivity is for a full discussion of the potential of model misfit and the hierarchical model description of discrepancy. Of course, again, a correct discrepancy term would solve everything. I have an example of this. I'm going to go pretty quickly through and probably skip some slides. We've looked at this in terms of a case of calibrating ocean model parameterization for an example here. The situation is we have a very simple computational framework. It's intended to model the ACC, Antarctic Circulating Current, and the notion is that we have a high resolution model that's eddy resolving, so we believe it has correct heat transport properties. We have a lower resolution model that does not resolve eddies, and we don't think is getting the right heat transport properties. And there's this parameter called the Gent-McWilliams GM parameterization, which is supposed to take up that effect. The GM in this case is a 2-parameter correction to the model. The goal is to try to calibrate that so that the properties of this model give us the similar properties of this model. We have a number of data types, potential temperature versus depth integrated over the whole domain with a black curve that's supposed to be the reference true value of the high resolution simulation, and some other ones that I won't go through in any detail at this point. Poleward heat transport, but these all represent quantities that we're trying to correct using this parameterization. We want to calibrate these things together. I still use my favorite tool is the one that I've invested a lot of time in, which is this GPMSA Bayesian model calibration tool, which is based on this exploration of the full Bayesian model calibration. This is a Kennedy O'Hagan style model inspired tool using Gaussian emulation, adding the full Bayesian treatment, so a number of parameters that can be inferred to correct the model, make the model fit as well as it can, using a multivariate response emulation in the linear basis, and importantly, adding the normal hierarchical distribution of calibration parameters associated with that multivariate response. In a case like this, these are the 2 parameters of this GM case, and what we're looking at is parameter distributions. We have 2 of the metrics that we're trying to match that I mentioned before. Each one of those metrics has a calibration independently, red and green, and in combination with a hierarchical model, it correctly finds, okay, it's a fairly well-fitting solution, kind of in the vicinity of those 2 curves. These are all scaled are all scaled arbitrarily because we're dealing with sample distributions, of course. As I start to add new calibration targets, we see that they don't match as well. The correct thing is going on with the model. I guess I haven't made enough of a point of what's the incorrect thing that could happen with these models. Is if you have the product likelihood distribution, you'd get the product of, say, the red, green, and blue distributions here, which would give you a fairly certain distribution but in the wrong place, instead of a relatively uncertain distribution, which seems more appropriate. A fourth type of data ends up with a calibration distribution on its own way over here. If you added that to a product likelihood space, you would incorrectly be very certain about a parameter value in that area, when what you want to do is have a fairly a diagnostic that tells you shouldn't be as certain as you think you might be if you go into this more naively. Of course, a final distribution, the full model has a discrepancy in it. In this case, it's saying this model, this parameter must be, or that data set associated with that parameter calibration must be very discrepant, and so it's very discounted. So observations about response modeling. This is a very tricky kind of area, I think, that needs to be. It has plenty of rooms for additional investigation and additional challenges. The inference in multiple responses is not straightforward when the data are in conflict with respect to the model. It's normally we go into a model. It's often the case where we will go into data collection thinking that, oh, we're just adding data to our conclusion. The more data we get, the more certain we'll be about our conclusion. That is definitely not always the case when we're dealing with real data and real experiments. The cost of diagnosing this can be very high. So in the theme of the workshop, cost and complexity. If you want to use a hierarchical model for this, which is a good diagnostic for doing it, these are very expensive kinds of models to fit, as is any other kind of diagnostic you might use in this area. And I should be explicit about, I think it's important to note that when you're dealing with these, say, a carbon capture kind of complexity of problem, it's not the case that you get to run an MC-MC chain arbitrarily long for as many times as you want. It's hard to get any samples out of that at all, and you might only get one chance to get one posterior distribution. Doing diagnostics in that kind of a situation can be very difficult. The danger of overlooking this investigation can lead to inappropriately tight estimates. And this is a comment about the common practice, which is the easy way to do things. In multivariate responses, you might choose a basis that's a linear weighting of the multivariate responses in order to model those weights. This can obscure this idea of a product likelihood relationship, but it certainly doesn't get rid of it. It's still lurking there under the hood, that you're considering all this data in a way that you're assuming a particular type of likelihood structure. Okay, that was the conclusion of that third part of the talk. I'll just leave my overall conclusions there. Clearly, uncertainty quantification is a critical aspect of learning about systems in science and engineering. It's getting harder rather than easier. And with reliance on the models comes the need to increase complexity of the analysis. We have multi-model, large numbers of correlated parameters, multiple experiments and complex connections of the component models to data, and multiple responses. And I say multi-response, but it's also multi-experiment. So a multiple response might be a single response gives you a collected field experiment that's a spatial field, or it could be that you're trying to calibrate the same model with two vastly different kind of experiments, which has similar implications, and taking advantage of the multiple types of observations. Okay, thank you. Look forward to talking to everybody at the workshop.
Are there any questions for our speakers? Please.
Jim,
Danny.
I'm not actually going to ask you a question. Not here anyway. But could you just put the model back up with the hierarchical discrepancy, just so that while other questions are going on, I can have another look at it.
Sure. Something in this area?
There.
Okay.
Thanks.
Yeah, sure.
Also,
Michael.
can I actually ask you a question?
Okay, thank you.
So, in the final examples you were looking at, okay, so you had parameters and you were calibrating them. Is your thinking that there is an unknown but true value of the parameter? For example, in the simple example, you had G. So we're supposed to think, do I get G right? Okay. When it comes to the ocean models, are there true values of the parameters? For example, as I think about how they model sort of like the oceans, depending on the degree of resolution, they don't want to get the water to behave as water, because at that degree of resolution it wouldn't actually work. Yeah? And I can easily imagine situations where some parameterizations might be good for some phenomena, for example, like top surface layers, and other parameters might be quite different, choices might be quite different for doing good understanding of like bottom surface things. So the notion of the calibration, everything comes together and you get a nice probability distribution. It's not clear to me that you'd expect that or you'd even want it, always.
Yes. Yeah, no, that's very true. So models aren't universal models. It very much depends on what you're actually interested in. And that varies across the domain. So what I'm showing, I think, is that that's a more insightful way to think about the problems with, say, climate models, or models that have multivariate response. I think climate models are the most familiar to us, where there might be one domain where it suggests a certain setting of parameters, another domain where it suggests another setting of parameters. The fraught aspect of that is that the notion of the project of simulating things is that you want to simulate the whole system correctly, and that gives you some confidence in extrapolation. When you have to tear the system apart and say, I could maybe do good at this part, maybe do good at that part, that doesn't give you a lot of confidence in being able to do extrapolation, which we want to do,
It may not
right?
be a lot of confidence, but it might still do a better job.
If you know that you're interested in shallow depth performance, I would think calibrate to shallow depth performance. That might be well. I'm gonna take that back partly, but yeah. So
Can I follow up?
Yeah.
I'm agreeing with Michael. I've got my wrong glasses. I've been reading over the weekend some stuff on the singular perturbation theory and boundary layer problem, because I'm trying to learn for another reason, trying to learn some of these more detailed things that happen at the boundaries. So there are, and of course, as the mathematicians, if I have to drill down into these boundary layers, they have different scales operate as you get closer and closer to them. That's my weekend's reading. So should not this is really exactly the same point. Should not the emulator technology reflect the precision of the reason why the mathematics models want to get? There's usually a specific reason. Understand the chaos, or understand some region where the tensile strength is threatened, or something. And so I'm agreeing that you can't have one discrepancy fits all. You need to really show where on your. It's a question of high fidelity. In some places you may be more high fidelity models, other places lower fidelity. Same point.
Sure. I might just tie that back to the initial, the first part or second part of the talk, where you have complicated model systems. And it's not enough to say we have a single model that describes this, we can collect as much data as we want, when we calibrate this we'll get the right answer. Really you're pointing out that there's a parameterization that works at shallow water. We might be able to inform something about that parameterization that doesn't come from just the full system parameterization, and you can learn more about, maybe there's a discrepancy component within there, and it's about teasing apart complex models into model systems. And therein lies a whole number of challenges. I'll leave it at that for now, but I'm sure there's a lot to follow up on there.
In the interest of keeping time, can we please continue the discussion later? I know that there's people who want to ask, but I will be grateful if we can continue later. So can we thank our speaker again?